Okay. We have in your TI-84 the way to calculate or to get the t-values. How do you do that? You just go to segment bars or distributions, and you are going to see t-PDF and t-CDF. Well, the t-CDF, the cumulative distribution function, is the one that is going to give you the probabilities, okay? As in any other distribution. And the inverse t, that is 2 on before the t-CDF, is going to give you the t-values, okay? For example, and probably in this chapter, the most important are the t-values, because the t-values are part of the confidence interval formula, okay? Next chapter we will see how to get the real t-values. Anyway, so for this chapter you can use the inverse t, hit enter, and it's going to ask you, the first thing it's going to ask you is the probability, okay? And which probability? This is the t-distribution, and this is the probability that the calculator is going to give you. For example, let's see the table. Let's look at the 31 degrees of freedom, and that probability over there is what? Is one tail. It's 0.025. Let's say that 0.025. Okay? So the inverse t, is any problem over there? Okay. Inverse t is going to give ask you the probability 0.25, then the degrees of freedom. In this case, 31, let's say. Okay? And it's going to give you what? 0.025, comma, 31. Enter. And it's going to give you negative 2.0395, which is 2.040 in your table. So it's, it's not exactly, but it's very, it's rounded to 3 decimal positions. Did you see that? So in your table is 2.040, and in your calculator is 2.0395, which is exactly the same.
Well, what are you doing on your calculator to get to that?
In order to do that, you are going to enter the left side of the probability, which is 0.025, for the 95% confidence level. And then comma 31. What?
I don't have inverse t.
You have TI-83, right?
No, I'm TI-84.
Where is inverse t?
It would be
Inverse t is in distributions,
Yeah.
and it's the number 3.
I have inverse norm.
Inverse what?
Norm. It's number 4. No, that's t.
No, that's number 4. Inverse t is number 4. You have TI-84, TI-83.
PDF and TCDF.
No.
Yeah. Yeah, you don't have it. TI-83 probably doesn't have it either. But anyways, well, you are going to have access to the T-tables anyway. But I just want to let you know that there are some, right now I know that there are some TI-84s that do not have that capability, but there are other that. This is TI-84 plus, probably that is wrong. Anyways. Okay, well, let's continue. The last part of the chapter is about to know what is the value of what is going on over there. Guys, if you don't want to be here, just leave, I already have you in my attendance. The last part of the chapter is about how to calculate the minimum sample size in order to get a particular margin of error. Okay? We already know the confidence level, but we need to know what is the minimum sample size in order to get a particular margin of error. Why do we want to do that? Because there are sometimes the tests that you are using for sampling are destructive, and you want to minimize those number of elements or number of products that you crash or you use. For example, if you are testing bullets, when you want to test the bullet, you have to fire the bullet in order to measure probably the speed or the performance or the accuracy or whatever you're trying to measure. So you want to minimize the number of elements that you destruct, or the minimum sample size, in order to get the particular margin of error. And that is pretty easy, because remember that for the confidence interval for the population mean is x bar plus or minus c of alpha divided by 2 sigma over square root of n, right? This is my margin of error. I have the margin of error that I want to get. What I don't have is my n. The only thing that we have to do is what? Substitute the n, or put the n in the one side of the equation, and it's going to be the margin of error is in the bottom, squared c squared sigma squared. Okay? That's exactly the same equation, but the n is going in the other side of the equation. So in order to do that, since this is dividing, you go to multiplying, square everything, and that is why the z is squared, the sigma is squared, and the margin of error is squared. For the confidence interval of the population proportion, you have p plus or minus c of alpha divided by 2 and the square root of p times 1 minus p divided by n. And this is my margin of error. So what has to be n? To just put this away, and my n is going to be the margin of error squared, z squared, p times 1 minus p, and p and 1 minus p are not squared. Why? Because in this side of the equation is already squared, so I square it to get my n, and this is it. That's it. That's it. And you need, after you do that, you have to round up. Always round up. If it's 3.75, it's 4. If it's 3.1, it's 4. It's always round up. That's it. Let's do a couple of problems. Problem 839. It says, determine the sample size needed to construct a 95, we have the confidence level. 95% confidence interval to estimate the population mean. So this is the one that we're going to use. This is for the mean, this is for the proportion. To estimate the population mean with sigma equal to 40 and the margin of error is equal to 6. Okay? So what do we need to do? Just apply this formula. So N is equal to Z squared, sigma squared, divided by the margin of error squared. What is my Z? If it's a 95% confidence, what is my Z? 1.96, so it's 1.96 squared times 40 squared divided by 6 squared. And that's it. So it's 1.96 squared divided by it gives you 170.74. So if I always round up, the minimum sample size has to be what? Round up 171. Round up, always. Okay? I mean, it's pretty easy. It's just this formula. And these formulas are in your book. They don't tell you how to do this, but I already told you how to do that. And for the proportion, let's do example, problem 841 that says a 99% confidence interval. I'm going to do it right here. 99% confidence interval. That's 41. P is equal to 0.4, and the margin of error is equal to 5%. That means it's equal to 0.05. Okay? But remember, what is the margin of error? The margin of error is how far away from the mean are you going? So this is my confidence interval, right? So my margin of error is half of the confidence interval. The margin of error is half of the confidence interval because we go for the X bar plus or minus the margin of error. Okay? Okay, so with this data, what we immediately do is to apply the formula. What is my Z for 99? C squared P times 1 minus P over margin of error squared. What is the C for 99? 2.575. So my N is equal to 2.575 squared times 0.4 times 0.6 divided by 0.05 squared. Just apply the formula, man. It's pretty easy. You just plug the numbers in the formula. And that is what? Okay. 2.7575 squared times 0.4 times 0.6 divided by whatever it is I got 636.54. So I have to use what? 637. This is the minimum sample size in order to acquire that particular margin of error. Always round up, so it's 636.54 goes to 637. Okay? What?
What's the answer?
That's the answer, 637.
Okay.
Because the answer was 636.54, and you always round up. You go to the next to be more sure.
So what if it's like 636.2?
637, always round up, always. It really doesn't matter if it's 0.1 or 0.2. You go up, always. Okay? Okay. And the last last part of the chapter is about finding the confidence intervals when the population is finite. Well, that cannot be simpler. The only thing that you have to do is to include in the formulas the finite population correction factor, which is what? The finite population correction factor, which is the square root of n minus n divided by n minus 1. That's it. There is nothing beyond that. So, for example, if you are using the confidence interval for the mu when sigma is known, you are going to use the formula x bar plus or minus z of alpha divided by 2 sigma over square root of n, right? That is the formula. But what happens if it's a finite population? You just start at the end, n minus n divided by n minus 1 square root. Okay? That's it. I mean, you just add at the end of the formula for the confidence intervals the finite population correction factor. There is nothing more than that. And when is a finite population? When do you have a finite population? When the sample size is greater than 5%. When n divided by n is greater than 0.5. When you have this situation, you need to use a finite population. Simpler cannot be.